So in the last video, we talked about how we could think about muscle activation, meaning the percentage of the maximum amount of force a muscle is capable of producing. We could think about that as being more or less equivalent to how much calcium ions are present in the area. And what I want to talk about now is the differentiation between muscle excitation and muscle activation. So let me erase this plot and write those two words out and explain what I mean. So, muscle excitation as compared to activation. So we can think about muscle excitation as being the electrical signal going to a muscle. How big of an electrical signal are you getting? Because you might imagine maybe there's multiple motor neurons or you can activate the motor neurons not at full capacity. So we could think about muscle activation as going from maybe 0 to 100%. And we can think about muscle excitation can go from 0 to 100%. Muscle activation, that's like the presence of calcium ions. We could think of that as going from 0 to 100%. And of course, these are closely related because excitation is the signal that tells the sarcoplasmic reticulum to dump out its calcium. And then when the electrical signal goes away, those calcium ions get pumped back into the sarcoplasmic reticulum by little pumps that exist on the surface here. But the subtle point is that there is a delay between when the electrical signal begins and when the calcium is pumped out. And there's also a delay, a slightly longer delay, from when the electrical signal ends and when the calcium gets pumped back in. So let me sketch out a different plot and show you what I mean. Let's make a plot of first. Let's just make it go from 0 to 100%. And I'm just going to plot a signal from the central nervous system. So let's say this is going to be excitation. So let's suppose you can do this artificially with like electrical current, but let's suppose your brain is not sending any signal to, let's maybe say your bicep muscle. And then it turns the bicep muscle on 100% for some amount of time, and then it immediately turns it off. Okay, so very simple signal. Turn the muscle on, keep it on for a while, turn it off. So that is the muscle excitation. Now, if we looked at the force production in the bicep muscle, maybe what's a good color to draw this? Let's do it in yellow. So I'm gonna do this as force production as a percentage of maximum force. So that it can also go from 0 to 100. And by the way, this x-axis here would be time, if that wasn't clear. So what's going to happen to the force production? Well, obviously, when there's no signal from the central nervous system, there's no muscle force. Here is what happens, though. When that excitation signal gets to the motor neuron, it transmits down to the sarcoplasmic reticulum, and the calcium starts getting dumped out through diffusion. So you start getting muscle force production, but you don't get it right away. There's a delay. There's a lag. And so what you get is something where muscle force production will ramp up like this. And then you get to, and I guess you might get to maximum a little bit earlier. So let me fix that. So after some delay, you get up to maximum, whatever the maximum muscle force you're going to produce is. You could think of this as activation. And when I'm saying excitation versus activation, what I'm talking about is electrical signal, which is in purple, versus the actual force production, which is in yellow. So after some little delay, so maybe we see short delay. Short delay between when the electrical signal reaches a muscle and when it starts producing maximum force. Then you get maximum force. Now, what happens right here? Well, the signal from your brain says turn the muscle off. So stop dumping calcium out from the sarcoplasmic reticulum. As you might guess, there's going to be a delay as well. But what's interesting about this delay is that it's a little bit longer. And the reason it's longer is just because it is slower to pump calcium back in across the sarcoplasmic reticulum because it's a chemistry diffusion thing. But essentially, the calcium in here, you can think of it as like bottled up and ready to go. And as soon as it gets this electrical signal, it just needs to diffuse out. Whereas when you pump it back in, it needs to be actively pumped back in across this membrane. Again, details of that, not super important. That's more of a physiology, biochemistry thing. What is important to know is going from muscle off to muscle on, there's a short delay between excitation and activation. And going from muscle on to muscle off is longer delay. Now, the difference between excitation and activation is going to be most relevant for highly explosive activities. So Olympic lifting, plyometrics, jumping, sprinting. And this is going to be less important for activities of daily living. So getting up out of your chair, walking up and down the steps, because you might imagine if the muscle signals are relatively long. So if this is some big long excitation signal, these delays are relatively small in comparison. But the big thing to take away from this is that going from receiving a neural signal from your central nervous system to producing force has some delay, and there's a delay going from turning your nervous system telling you to turn off a muscle and the muscle actually ceasing its force production. And the delay to turn a muscle off is longer than the delay to turn a muscle on. So those are the big three things to take away about excitation and activation.